Hi students, this is a quick review video of chapter 4.1, which is on work and power. So to get us started with a definition and the equation of work, work is force times distance with a unit of joules. The whole definition is really to use a force to move an object in the direction of that force. Essentially, it's applying energy to move an object, right? It's force times distance. So one of the examples that we gave is if you have, and this is my mountain, right here it is lined with snow up at the top, you've got two ways to get from point A to point B. You can go directly up, right? Or you can take the roundabout route back around the mountain, 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 and finally up to point B. Route number one has a short distance, but a lot of force. Route number two has a long distance, but a short force. Sorry, long distance, but less force. That makes a little bit more sense. So in these two examples here, the same work is done. So whether we are talking about going straight up the mountain, which would be this example right here, going straight up the mountain, that's route number one, or taking this path along here, then up here, all that way, that's route number two. Both of them are the same work, which means that you expend the same amount of energy to get to the top. It's just that route number two is going to take you a lot longer. It's going to take a much longer distance to get there. So if we're talking about which one is easier, number two overall, right, in any one instant is going to be easier because this whole time you're going up a slight incline all the way to the top. Option number one, you go straight to the top of the mountain, really, really hard, all at once, a lot of force. So route number one might only take you 30 minutes, whereas this one, route number two, might take you 2 hours. Now, if both of them are the same work, are you going to be more or less tired after 2 hours have passed on route number two or route number one? If we're thinking about this the right way, if it's the same work and therefore the same energy, in that amount of time, the same amount of time, you will be equally as tired. However, if we're just looking at the 30-minute period, the person taking route number two in 30 minutes will only be up to about here. But they won't be very tired because they're not expending a lot of energy in any one moment. In 30 minutes, the person taking route number one will have gotten all the way up there, but will be quite tired. So what we're seeing here, I'm going to kind of scoot down a little bit. What we're seeing here is that force is essentially a measure of difficulty, right? It's how hard it is to get the work done. The distance, there's no really other way to describe that, is just distance, right? It's how far you're going to travel. It's how long it's going to take. However, work is kind of the job done. So if we want to do that job more easily in any one instant, we're going to try to limit the force. And if we decrease the force, that means we have to increase the distance, and the work will be the same. So whether it's climbing a mountain or moving boxes into the back of a pickup truck, if you want to make that job easier, you're going to increase the distance. So you might use a ramp, right? It might be a shorter distance to pick up that 300-pound box right into the back of the pickup truck, but you might not be able to do that. You might not be able to pick up a 300 or 400-pound object and put it in the back of a pickup truck. So instead, now we get to see my wonderful car. Here's my, right, there's my pickup truck. Oh God. Here we go. All right, Ford F-150 right here. Okay, here's the door, here's Mr. Cowman, right? He's yelling at people, hey kids, get that, heavy object into the back of the truck. You've got two options. You can pick it up and put it right into the box, or into the back of the pickup truck. That's option A. Or you can drag it, here's the box, you can drag it up here. That's option B. If it's 400 pounds, you're most likely going to choose option B. Slightly longer distance, but less force in any one instant. So let's skip over here to power for a second. Power is the equation that takes time into account. So it is work divided by time, or how quickly you do work. You do work. Or technically, how quickly you get the job done. Right? The unit is going to be watts. So this is the only one of the two that really takes time into account. Right? Theoretically, if you are taking option number 2 here, and it takes you 2 hours to do the same work as option number 1, which one requires more power? Ding, ding, ding. Option number 1. So if you want to expend less power, meaning do the same work in a longer time, you're going to take option number 2. It's the same reason, it's the same reasoning that we were using when we're talking over here about force being difficulty, right? When we're talking about some limitations to all of this, right? This is where we are here. These are not necessarily in your notes. So here is a woman. This is called a clean and a jerk. Clean and jerk, or a clean and press, right? She gets the weights. They started out down here, right? They used to be down here, and she gets them first up to about here, and then pushes them up to here, right? A lot of work, literally and figuratively. That's a hard job to do. If she were to stand up and then hold those weights overhead, where they were just sitting right here, is she doing any work? If they're not moving, no movement equals no work. Now, you're probably saying, well, clearly she's holding, 200, 300 pounds over her head. That is a lot of work used in the figurative daily sense, right? Holding 300 pounds over your head is really, really hard. However, technically, since we are talking about mechanical work, she's not doing any when it just sits over her head like that. The only time she does work is when she moves it from the ground up to her shoulders and then overhead, right? A, B, and C. A, she does work. B, she does work. C, she does no work when she's holding it over her head. So that's kind of the limitation, is that must be moving and in direction of the force. So, for example, when we're talking about, we were in class and we had a big box on the floor, and we needed to pick it up. That is doing work. But when we were then talking about walking it this way, we were no longer doing work. And the reason that was the case is because what we were fighting, the force that we were fighting, was the weight of the object, the force due to gravity. So when we picked it up, and gravity was trying to pull it down, and we put a force pushing it or pulling it up, the box also moved up. But when we were walking across the floor with it, we are not putting force on the box in the same direction as it's moving. We are putting a force on the box upwards to keep it from falling down, and then we are walking forwards. Technically, when we're walking, our legs are doing work on the earth. So we always need to keep in mind what we are doing work on, what object we are talking about. And if we are talking about this object here, the box, we are only doing work on the box when we are picking it up, not when we're holding it and not when we're walking with it, because then we're applying forces to different objects and in different directions. So two things that were in the reading that we haven't talked about a lot were kinetic energy and potential energy. Basically, kinetic energy is energy in motion, and potential energy is stored energy, or the ability to do work. So for instance, the number one example of kinetic and potential energy is a rolling ball versus a ball at the top of a hill. So if we have, once again, here's our sloping hill, we have a ball that's up here, and it's just sitting here. It hasn't moved yet. It has potential energy. It has the potential to move in the direction of a force. It has the potential to go down this way. As soon as it is actually rolling down the hill, it has kinetic energy. It's actually expending energy in a direction of its force. It's rolling downwards. If it hits you, it passes on that kinetic energy to your body, right? So if you have something at the top of the hill, if you're holding a weight, if you're about to throw it, if your muscles are tensed, about to throw a ball, that is potential energy. As soon as that ball is moving, you've transferred the potential energy into that ball, and it now has kinetic energy. So to just briefly summarize everything that we've talked about, work is force times distance. It does not take time into account. No time. Right? So as we were climbing the stairs, whether you climbed them quickly or whether you climbed them slowly, you were moving the same distance every time, and it was the same force, meaning your weight. Each time it was the same work, whether it was quick and slow. Another thing to remember is with work is that it has to move in the direction of the force, and there must actually be movement. Like with this weightlifter here, if she's just holding that weight overhead, she is not doing any work, even though it is really, really difficult. If we want to reduce how difficult something is when we're doing work, we increase the distance, because that means that in any 1 second, we're expending less force. Power is how quickly you do work. Work divided by time. This is where time comes into account. We need to always remember the limitations, right? 1, that it must be moving, and 2, that it must be moving in the direction of the force. So this does not take our bodies into account. We're talking about mechanical energy only. Obviously, holding a weight overhead is still really, really, really hard, but technically, by definition, it is not mechanical work. Kinetic energy is energy in motion, and potential energy is that stored energy right here, the potential to do work. And once it starts rolling, it's kinetic, it's now doing work. Please shoot me an email if you've got any questions.